Okay, let's start with a really wild thought experiment. What if tonight, poof, every single human on Earth just vanished? I know, it's sci-fi stuff, but stick with me. By exploring this idea, we can actually use the planet's own physics to get a handle on the true scale of our impact.
Just try to imagine it for a second. One moment, the world is humming with all our noise. Cars, factories, cities buzzing. And the next, total silence. So, what happens to the climate that we've so dramatically reshaped? How long would our signature, our fingerprint, actually last? And just to be clear, this isn't about doom and gloom. Not at all. It's really a journey to understand the deep, and I mean deep, lasting marks we've left on our planet. All right, let's dive right in. Before we can talk about how the Earth heals, we kind of have to do a checkup, right? We need a clear diagnosis of its condition right now. We've pushed the system hard and fast. So let's take a look at the planet's vital signs. So, first up, the air itself. The amount of carbon dioxide in the atmosphere is now sitting at around 420 parts per million. Now, that number might not mean much on its own, but get this, that's a 50% jump from where it was before the Industrial Revolution really kicked off. 50%. That's a huge change. And all that extra CO2, well, it acts like a blanket, trapping heat. The result of that? The planet's average temperature is already up by about 1.2 degrees Celsius compared to, say, the late 1800s. And I know 1.2 degrees doesn't sound like a lot, but believe me, for a planetary system, it has enormous consequences.
Okay, and this right here is probably the most important piece of the puzzle for our whole thought experiment. See, unlike smoke from a campfire that just blows away, CO2, it builds up, it lingers, it has incredible staying power. And the story of how it eventually gets removed, well, it's a tale of two very, very different speeds.
So let me introduce you to Earth's cleanup crew. They're called carbon sinks. Now, you've got your fast-acting crew. Think of forests, breathing it in, and the surface of the ocean soaking it up. They get to work right away. But then you have the slow, deep crew. We're talking about the vast, deep ocean and the super slow weathering of rocks. These guys work on a totally different timescale, like geological time. This chart really shows you what I'm talking about, that long, long tail of our emissions. Look, after we vanish and the emissions stop, you can see about half of that extra CO2 gets pulled out in the first 100 years or so. That's the fast crew doing its job. Then, over the next 900 years, another 30% gets absorbed. But what about that last chunk, that stubborn final 20%? Well, that sticks around for thousands and thousands of years. This is such a great analogy. It just perfectly captures how permanent this is. Think about it. CO2 isn't like a campfire that's cold by morning. It's way more like a tattoo. You can fade a tattoo, sure, but it takes a long, long time. And even then, a ghost of it can remain. It's pretty much the same deal for the carbon we've pumped into the sky. Okay, so keeping all that in mind, let's start the clock. Click. Humanity is gone. What happens in those first 50 years, the first few decades of sudden planetary silence? Well, some changes are almost immediate. Methane, for instance, it's a really powerful greenhouse gas, but it doesn't stick around for long. Its levels would drop like a rock within just a few decades. And all that smog, that haze and soot from our pollution, what scientists call aerosols, that stuff literally gets washed out of the sky by rain in a matter of weeks. But here's where it gets really interesting. A weird twist. All that pollution, those aerosols we just talked about, they were actually doing something else. They were reflecting sunlight back into space, creating this cooling mask. So once all that gunk washes out of the sky, the mask comes off. And ironically, the very first thing that happens is the planet gets a little bit hotter. It might tick up by about another 0.3 degrees before the temperature finally levels off. And this, right here, is the key finding for the atmosphere. This is huge. Once the emissions stop, the warming stops. The temperature doesn't just keep climbing and climbing. It finds a new, hotter baseline, and it just stays there. The fever, essentially, breaks. But, and this is a big but, while the atmosphere finds its new balance pretty quickly, another massive part of the Earth system is just getting warmed up. The oceans. They are like a giant, slow-moving freight train. They operate on a much, much slower clock. This is honestly one of the most important things to get about climate science. The air, it's fickle. It can change temperature pretty fast. But the oceans have this immense thermal inertia. All that means is they're incredibly slow to heat up, and they're just as slow to cool back down. They soak up heat and just hold onto it for a very, very long time. So that begs the question, why do the seas keep rising even after the air temperature has stopped going up? Well, there are two main reasons. First up is something called thermal expansion. Simple physics. When water gets warmer, it expands. And the oceans have already absorbed a truly staggering amount of heat, so they're just going to keep on expanding for centuries. And second, there's the ice melt that's already baked in. Glaciers, parts of the ice sheets, they've already passed a tipping point. They're going to continue to melt and shed water into the ocean long, long after we're out of the picture. Okay, let's hit the fast forward button. Way forward. We're zooming past the first 1,000 years. The air temperature is stable, the seas are still creeping up. Now we enter a totally new phase, where the slow, deep, powerful forces of the planet itself take over the final cleanup. So over thousands and thousands of years, the deep ocean is still churning away, slowly pulling down more of that leftover CO2. But get this. Even after 10,000 years, that stubborn 20% of our carbon tattoo is still hanging out in the atmosphere. To get rid of that, you need geology to step in. We're talking about the incredibly slow process of rocks weathering, washing minerals into the sea. Minerals that eventually form new rock on the ocean floor, locking that carbon away. We are now talking about 100,000-year timescales. It's just mind-boggling. I love this idea. It's like on these 10,000-year timescales, geology becomes the main climate activist. The fast systems, the plants and the surface ocean, they did their part. But now, it's up to the planet's own deep geologic cycles. They're the only things powerful enough to finish the job. So, we've covered the air, the oceans, the rocks. But what about life? What about all the biodiversity, the species we've pushed to the brink or over it? Well, when it comes to recovery, this clock is by far the slowest of them all. If we look at the fossil record, after past mass extinctions, we get a really sobering benchmark. It usually takes something like 3 to 5 million years just for the total number of species to bounce back. And that's just the number. To rebuild the complex, intricate ecosystems we've damaged, that could take 10 million years, maybe even more. That is the true depth of our biological fingerprint. Okay. Wow. So after that journey through deep, deep time, what's the point? What does it all mean for us? Let's bring all these different recovery clocks together and figure out what the real takeaway is for us. Right here, right now. This table really lays it all out, doesn't it? It shows that the word recovery means totally different things depending on what you're looking at. Methane? Poof, gone in 50 years. The global temperature? It stops rising in decades, but it stays hot for over 1,000 years. But then you look at atmospheric CO2, sea level rise, and especially biodiversity, and suddenly we're talking about healing on timescales that are they're almost impossible for us to even wrap our heads around. And that, right there, gets to the absolute heart of the matter. The planet itself, it isn't really in danger. Earth has survived asteroid impacts, for crying out loud. In the long run, in 100,000 years, it's going to be fine. But our civilization doesn't operate on that timescale. Our cities, our economies, our food systems, they all depend on a stable climate over the next 50 to 200 years. So the whole idea of saving the planet is a bit of a misnomer. We're not trying to save the planet. We're trying to save a version of the planet that is stable enough for us to thrive on. So this whole thought experiment, this whole journey, it brings us to one final, crucial question. The science is pretty clear. If we vanished, the Earth would eventually heal on its own, slow, almost alien timescale. But that's the science fiction version. The real question is for us. It isn't, can the Earth recover from us? It's, can we be smart enough to recover from ourselves while we're still here to enjoy the view? That's the real challenge. That's the real story.